We'll start the next example off with a slightly different approach. Really looking at the same steps, just ordering them differently. But we have the same type of problem. We're given a function with no domain restrictions. We want to determine if any absolute extrema exist. The first thing that we're going to do, because it'll make our next step a little bit easier, is to add these two expressions together. So if we think of that first term as x over 1, then x over 1 and 4 over x, our common denominator is x. So this would have to become x squared over x plus 4 over x. Then adding those together would give us x squared plus 4 over x. So we've rewritten the original function in a slightly different form. And what we're going to do this time is start off by taking the limit as x goes to infinity and negative infinity. So we're going to start off by considering end behavior. So all that matters with end behavior is just the dominant term in the numerator and denominator. So this will become the limit as x approaches infinity of x squared over x, or the limit as x approaches infinity of x. So x is approaching infinity, we're plugging in larger and larger values, which means this limit is headed to positive infinity. We'll also consider the limit as x approaches negative infinity of x. So in this case, we're plugging in larger and larger negative numbers, so overall smaller and smaller numbers. So this is headed to negative infinity. So when we take the limit as x approaches infinity, so part of that end behavior, and we get positive infinity, that means there's no absolute maximum. And when we get the other end behavior to be negative infinity, that means there's no absolute minimum. So regardless of what critical values we might find to consider, we already know that we won't have an absolute max, we won't have an absolute minimum because of the end behavior. So by starting off considering those limits, we can actually just state that no absolute extrema occur. There's no need to get into first derivative test, second derivative test. We don't have to worry about classifying any of those critical values because these two results already give us that definitive answer. Our last example is just a little bit different. In this case, we do have a domain restriction. We're considering this function on the interval from 0, including 0, up to infinity. So we do still want to consider the end behavior as x approaches infinity. So only considering our dominant term, we'll take the limit of 3x squared, which in this case will equal positive infinity, telling us that there is no absolute maximum. But we do have this domain restriction, so we're not going to consider the end behavior as x goes to negative infinity because we're cutting our function off at 0 on the low end. So then what we need to do is take the derivative of our function, find any critical values, and evaluate the original function at those critical values and this one closed end of our interval. So our first derivative in this case will be 6x minus 24, which equals 0. Setting that equal to 0 then will give us a value of x equals 4 as our lone critical value. So now we have a critical value to consider and our left endpoint, since that interval is closed on the left end. So what we'll do is go back to the original function and evaluate n of 0, which would be 0 minus 0 plus 5, and evaluate the original function at 4. So 3 times 4 squared minus 24 times 4 plus 5 will give us negative 43. In this case, the smallest of those two values occurs at x equals 4. So we know we have an absolute minimum at n of 4, and that specific function value is negative 43. So in this case, we don't consider n of 0 equal to 5 as an absolute maximum because the end behavior, that limit as x goes to infinity, approaches infinity, so that already rules out the possibility of having an absolute maximum. Our function is taking on larger and larger values, so 5 doesn't represent the largest value it will take on.